Put some sunlight in here.
Boy.
Get anything without.
Yeah,
That's good. All right, so I hope everyone had a good break. But of course, fun never stops. So we do have a homework assignment due on Thursday. There'll be the next one coming in 2 weeks. 2 weeks assignment.
Is this number 4 or 5?
Whatever, I don't know what number it is, the one that's, there's only one that.
It's only the middle one. Are there still only 6?
No, there is, so there is, that's number 6, so this is number 5. That's number 6. There'll be a extra credit assignment, but no, not required, but I want to give people opportunity to work on some of the things that we're going to be talking about. And then there's the final project. The final project will be a project that will involve the theory and study of quantum trajectories, which we'll be studying at the latter part of this unit on open quantum systems. And it'll involve doing some simulation of open quantum systems based on the quantum trajectory method. So it'll involve some numerics as well, okay? So there'll be enough time after this problem for you to get started, but we won't really get to that material until a little bit later, okay? All right, so as advertised, what we'll be discussing for the remainder of the semester is the physics of open quantum systems, okay? Now, we've studied this already to some degree in the last semester. And we saw, what do we mean by an open quantum system? What constitutes an open quantum system? So we had, different examples of dynamical evolution that we see in physics, right? I mean, if I think about a two-level atom. In vacuum. So if I have a two-level atom in the vacuum, I might start it in the excited state, and the state of the field is in the vacuum. Okay, so my initial state is, say, I prepare the atom in some excited state, and later it's in the vacuum. Okay, at the initial time. Okay, and now I ask you, what is the probability of being in the excited state at a later time? And what is it as a function of time?
The Hamiltonian T, right?
Well, the probability.
Oh, it's just minus gamma.
Yeah.
Or is that just as to decay? So
Yeah,
you
well,
assume it
it can decay to the ground, to the solid state, and there's some spontaneous emission. That's the probability as a function of time. Okay. In contrast, if we think about this in a perfect cavity, where the cavity mode is tuned to be on resonance with the two-level atom's Bohr frequency. So if this is with a Q of infinity, it's a perfect cavity, and I prepare the atom in excited state, and there's the vacuum of the single mode. So I have some cavity mode which is on resonance with the two-level atom. What is the probability of being excited state as a function of time in this case? It'll fluctuate. It will oscillate, right? And it'll oscillate with some rate that we call the vacuum-Rabi oscillation rate. So these are two very different evolutions given the same kind of initial condition, right? You know, some of the properties we see here is that this evolution is irreversible. Even if I started in some superposition of ground and excited, at a later time, I will be in the ground state and I cannot reversibly get back to the superposition. So I've lost information in some sense. So the evolution dynamics are irreversible and they're dissipative. Meaning that the energy, I had some initial energy in the system, and now energy is not conserved. The energy went somewhere, it went into the spontaneously emitted photon, but if I just think about the atom itself, I've lost energy, okay? Whereas in this case, I have reversible dynamics, and I have energy conservation. So that's this kind of system we would call an open system, and this kind of system, I'm sorry, and this one we would call a closed quantum system, okay? So, I mean, where does this kind of irreversible dynamics come from? From whence does that arise? Why? When we know that the microscopic dynamics described by the Hamiltonian of the whole system are time reversal invariant. You know, I was all about time reversal invariance and retrocausality. What's different in the system versus this system? Why does this guy behave this way and this reversibly?
You got any vacuum interaction?
Well, this is also interacting with the vacuum. There's a vacuum mode that.
Right, but you're being driven by that one.
Well, I mean, they're both the same initial condition. They're both driven by vacuum. Initially, I mean, if there was no coupling to the vacuum, the atom would stay in the excited state. So the coupling to the vacuum is essential for both of these phenomena. Yeah, Ben.
In one case, you can couple to the environment.
Well, yeah, so, okay, but what does that mean? I mean, you know, they're both, in some sense, as I say, they're both the same situation. We have the vacuum coupled to the atom, and this guy, so what's, yeah?
Because the cavity is perfect, we can assume that the escape decay rate is zero?
Yeah, so there's no, it's true, we're not allowing any leakage out of the cavity. That would definitely be irreversible in that case. But the underlying difference between the system is the number of degrees of freedom, okay? So in the case of the perfect cavity, the James-Cummings model, we have the atom plus one mode, okay? So that's kind of equivalent to two coupled oscillators. You can think about the two-level atom as a kind of oscillator that can Rabi oscillate, and we have one mode. It's the harmonic oscillator of one mode. It's like having a situation where I have two pendula. With some coupling constant between them. And if I were to put excitation in one of these modes, one of these pendula, what's going to happen? It'll transfer to the other one, it'll start oscillating, and then back and forth, right? So we'll get excitation going from one degree of freedom to the other and back with a simple dynamic. And if I had multiple coupled pendula, and I excited, just pulled on this one, what's going to happen? Well, it's going to propagate, and then it's going to propagate back. And there'll be a revival time. And that revival time depends on the number of pendula. Each pendulum is a degree of freedom. So this one degree of freedom is coupled to many degrees of freedom. And there'll be some recurrence time. And that recurrence time gets larger and larger and larger the more degrees of freedom this one system is coupled to. And in fact, if I ultimately went to some approximate limit of a uncountably infinite number of degrees of freedom, like a field, I can think about a rod which has modes of sound waves that propagate through it. And if I, took a little hammer, if I had a hammer, and I knocked it on this thing, then we know that would just propagate away. And the degree to which this was an infinite rod, it would never come back. And so we would have effectively irreversible dynamics. So an important aspect of what kind of distinguishes the idea of a bipartite, so these are both bipartite systems. One part is the atom, the other part is the quantum field. But in one case, I'm restricting the number of degrees of freedom to 1 here, and in this case, I have an uncountably infinite number of modes of the vacuum electromagnetic field without boundary conditions that can couple. And it's analogous to this. Okay, so that's really the story.
They didn't just get lost.
It just goes into, there's many different excitations, all these modes, and it just goes on. It doesn't have the recurrence time. It basically goes to infinity. Okay.
Right, but that's only if you look at the one. Like if you look at the whole thing, of course,
Sure.
it remains up.
Yeah.
It remains closed.
We'll come back to that story.
Right.
Yeah. So what we have in this situation, thus, and this, is we think about an open quantum system. I have some quantum system, which is one part of our world, the thing we're interested in. It could be a superconducting quantum computer. It could be one atom. It could be whatever is the quantum system that we're interested in. And the other part, everything else that couples to it, we call the environment. Okay? Which is, and although I didn't draw it quite in the most evocative way, this is a system which has some reasonable number of degrees of freedom that we can want to track it. I mean, even, of course, we know if we have, the Hilbert space can still grow exponentially. Even if I have 100 qubits, I have 2 to the 100 dimensional Hilbert space, but that's, we're doing our best to try to control within that in the best way we can. But the environment is often thought about in a thermodynamic sense, a sense of being like an Avogadro's number or more macroscopic kind of thing, which couples to the system. And so often in that kind, sometimes the environment is called the bath. In the sort of thermodynamic sense that I have, this engine and I put it in a heat bath, right? That's the environment, or it's sometimes called the reservoir in a similar spirit to that, okay? And so some of the hallmarks of this, and so the idea is that, I might have energy or excitations in the system and they go into the environment, but they don't come back, okay? They get lost in this reservoir, they get lost in this Avogadro's number or more, an uncountably infinite number of degrees of freedom in some approximate sense. And so some of the hallmarks of that, as we just said, is that we get, we can have the idea of energy dissipation and relaxation. We can have equilibration. That is to say, if this is at some temperature T, then we expect then maybe some of the energy goes from the environment to the system. And in this case, when I have the vacuum, that's a T equals 0 environment, that is at 0 temperature. we'll come back to think about black body radiation in a little bit. But these are processes that happen through this kind of open system dynamic. We can have, of course, entropy increase. I could have a situation where if this is at some finite temperature and this was at, say, 0 temperature to some good approximation, I prepared the atom close to a pure state. It's never perfect, you can't do that, but close enough. Then if it's in contact, say, with black body radiation, we know that the atom will come to a thermal state in equilibrium with the environment. So these are kind of things that are true in classical statistical physics. We can think about, you know, the approach to equilibrium in some dynamical system in classical statistical mechanics as well. We don't typically teach that. Typically, you learn about equilibrium, thermodynamics. Everything is already in equilibrium. We don't learn about the dynamics by which things come to equilibrium, but we could, and we did, what people do. But there's another aspect of this which is more uniquely quantum, which is decoherence, which is the loss of quantum coherence. So if we have the situation where entropy is increasing, then we're losing coherence. We're losing quantum coherence generally in the system, right? And the loss of quantum coherence is something which we have to live with. I mean, the fact that we don't see quantum effects in the macroscopic world is 100% understood by this, decoherence. Decoherence is a fact of life. You never thought you'd hear about the facts of life from me, but I'm telling you about them, right? And moreover, it's important in understanding, as we will talk about, the so-called quantum to classical transition. That is to say, why does, at the macroscopic world, is Newton's laws, or it may be, Newton's laws with friction, do a good job of explaining the dynamics that we see in the macroscopic world and not the Schrödinger equation. And how do we recover classical dynamics from a fundamentally quantum description? So that's an important thing. And the other thing, as we'll see, is that it's an important ingredient in measurement theory. How we understand quantum measurements. There's an intimate relationship, as we're going to learn about, between measurement theory and open quantum systems. We'll talk a little bit about that today, okay?
I just have
Yes.
a problem with the quantum to work to classical.
Yeah,
Like, you don't actually, you just like, I'm not very familiar, maybe we'll get familiar.
Well,
It's just that it just like, gets statistical, right? It doesn't,
Yeah,
you don't derive Newton's laws out of those
well, you
things.
can get
Make
something,
it
you can get
deterministic.
something with effectively where the uncertain, you never get perfect, obviously, because there's always quantum uncertainty. But those fluctuations can be minimal, right? Because Planck's constant is so small compared to the classical action. We'll talk about it more in detail, but so we don't get perfect deterministic evolution, but we can get something that is well approximated, where the fluctuations around the mean of what we would project for a trajectory are so tiny that they're irrelevant. Yeah.
If you think of physics of thermodynamics, which is
Yeah.
then we can think of all energy is constant or temperatures constant
Yeah.
or particle numbers constant,
Sure, absolutely. All of the ensembles that we learn about. I mean, there is a field called quantum thermodynamics, which tries to study the ways in which quantum systems might allow you to do some things differently than in those same thermodynamic descriptions that we have with classical physics, and how work and energy, what they mean at the quantum level. It's a pretty subtle business. I'm not very well versed in it, I don't know it well, but it is a very active field of study.
Just one more.
Yeah.
Will we consider particle exchange from our system?
At the moment, I mean, the descriptions we'll see are very general, and we'll talk about them without the specificity of what it is. But typically, no, we're typically thinking about there are some degrees of freedom that we want to cordon off that we're calling the system, and other degrees of freedom, the rest is the environment. So particle exchange is not quite in that same spirit. All right, so what is the connection? There's one other aspect of this that I want to emphasize that's critical in this whole story, which is different again from what we thought about from a kind of classical open systems theory, is entanglement. Entanglement plays a very, very important role, which is one of the reasons we studied it in just before spring break. Thinking about the way in which quantum coherence is lost, the way in which decoherence happens. As we remember, one of the hallmarks and important aspects of entanglement is that if two systems are entangled, then the subsystem has lost information. Information is in the whole, it's no longer in the pieces. And that loss of information is entropy. That's what entropy is. It's missing information, quantified, say, by Shannon as the Shannon entropy, which is equivalent to entropy that Boltzmann defined without the Boltzmann constant. And so the theory of entropy increase, decoherence, and quantum measurement theory are all intimately related to the entanglement dynamics between the system and the rest of the world, okay? And that's something different than we have in classical thermodynamics, okay? All right, excellent. Let me see what I missed. Okay, good. So, so with that said, we're going to speak for the next few lectures about sort of the formal theory of open quantum systems, okay? And so we want to think about the dynamics of the quantum system when it is in contact with the environment, but we're only interested in the dynamics of the system. We're not interested in the dynamics of everything, okay? As Alejandro mentioned, if everything in the universe were included, then we have unitary dynamics as far as we know, unless, things are lost in black holes or, maybe. All right, so, so when we think about that, we have what we call a quantum channel. A quantum channel is a more general dynamic on a quantum system. So the quantum channel is something which I'll call script EE, which takes some input state of the system, okay, to some output state. So it's a map on quantum states. And generally, quantum states are treated as density operators, okay? They might have some initial impurity, all right? And so what we want is that this to be a physical state. That's to say that this thing should be permission, if the input state is a physical state, and it should be positive, right? You should have only non-negative eigenvalues. Okay, so that's what we mean by a quantum map, something that is some dynamic. An example of this is unitary dynamics. That's a quantum map, right? It takes the input state to the output state through a unitary evolution. But a more general open quantum system dynamics are not unitary, okay? So a general, this is unitary evolution. But a more general open quantum system evolution is not unitary, okay? Now we can formally describe it in the kind of spirit of what Alejandro was saying. We could say there is a, we can consider the joint Hilbert space of the system in the environment. This is the Hilbert space, not the Hamilton. Okay, which we think about as a bipartite system. And at time t equals 0, there's some state of the joint system. Okay. And if this is everything in the universe, if everything that's not the system we're calling the environment, absolutely everything, then the dynamics of this is unitary, right? So there's some joint unitary evolution on the whole thing, on the system and environment together, okay? So let's say this is over some time. So given this, my question to you is, what is the state of the system at a later time, given this?
Trace over the environment.
Trace over the environment. So this is the most general description of a quantum map, okay? It looks kind of messy. It doesn't really have very much utility in this form yet, okay? Now there's a very important special case that we consider truly important, which is to assume that at the initial time that we're interested in, that the joint system factorizes. Okay? So that won't generally be true, but it's a case that we're very interested in, and we'll see why as in the next lecture or so. But, you know, it's kind of like the problem that we started with in exciting the atom into the excited state, and we did it in a way that it was uncorrelated to the electromagnetic field, and they were in a product state at the initial time. Yes?
Even if it's not in the state, we can still engineer our system.
Well, I think it's more tricky. I mean, it depends what, you know, how, I mean, there's different aspects of this, Omar. I mean, there's what we're doing in quantum controlling systems versus what might happen in a natural setting.
Like for example, as a quantum computer,
Yeah.
I can just reset the whole.
I could try, yes, yes. Okay, so in this special case, and in particular, although we'll come back to this later, we'll look at this in a similar spirit to what we did with the cavity. We'll take the environment, although I said it could be a finite temperature, but we'll come back to that problem a little bit later. We'll just say that this guy is in some pure state, which I'll call the fiducial state of the environment. Okay, so there's some in the case, as in the case, the environment was in the vacuum. Okay, it seems a little odd to put the environment in a pure state, because we just said this is like a thermodynamic thing, like a bath at a finite temperature. And we'll come back to that, why we can get away with this. Certainly in the case that we were talking about, the atom interact at optical fields at room temperature, you know, there's no thermal photons around that we care about, so we can treat it in this way, okay? It's a mathematical thing as well, and we'll come back when we treat this. So in this context, the quantum channel is defined by two things. What the interaction between the system environment is, and this fiducial state. That defines the channel, okay? And how the channel acts on the system. So let's plug in this ansatz into this expression, okay? It says that at a later time, I trace over the environment of this guy only doesn't act on the system, it only acts on operators that involve the environment. Okay? So I just separated the bracket in that way. Okay? So now I have to take the trace over the environment. And so I'm just going to do that with respect to some orthonormal basis of states in the environment. And so the trace is just the diagonal matrix elements of this with respect to the environment. So this is the sum. So I'm going to define a set of states I'll call the mu, which is a basis for the Hilbert space of the environment. And thus the trace looks like this. I sum over the diagonal matrix elements, which is the basis elements, mu, u, s, e, 0, rho, s at 0, 0, e, u, dagger, s, e, d. Okay. So now, when we look at these objects, this is what we call a partial matrix element, because this operator is an operator that's jointly on both the system and the environment. And I'm only taking a matrix element with respect to the environmental degrees of freedom. So this thing is not a number, it's an operator, and that operator acts solely on the system, okay? I'm gonna call it the measurement operator, or what is sometimes known as the Krauss operator, okay? We'll call it M, sometimes it's called K. I like M because it's really related, we'll see, to measurements, so I call it the measurement operator. It's also called the Krauss operator. And this guy here is mu dagger. And this is incredibly important. Something everyone should know, I wish we'd teach it earlier, is the idea of a Krauss map. So what we have learned is that when we have a general quantum channel with this factorization at the end, then the output state is given by what we call a Krauss map. Where these operators M are these partial matrix elements of the interaction Hamiltonian, or interaction unitary, starting in the fiducial state and ending in this particular basis state. And this operator is called the Krauss operator. Or sometimes a measurement operator. The connection to measurement will come a little bit later. Okay. What can we say about the Krauss operator? Is the Krauss operator a unitary operator? Not necessarily, but could it be? It could be. So if the entangling interaction factorized, okay, then the Krauss operator here is going to be this matrix element, which is some complex number, times a unitary. And that complex number will cancel on both cases. So if this is the case, then what we would just get is that we would get unitary evolution. So if we had a separable interaction, then it would be unitary evolution. In some sense, the environment learns nothing about the system. There's no coupling between the system and the environment, and they just evolve and go their separate way. You need coupling between the system and the environment. So if this is not true, then it's entangling, then mu is not unitary. Okay. However, in the way that we've just, the way we've described this general quantum map, even though it's not unitary, it's trace preserving. That is, if I look at the trace of this guy, and using the cyclic property of trace, I get this. Okay? But if this is going to be, since my unitary dynamics as for the whole system cannot change the trace, this must be 1. Which implies that the sum of mu dagger mu has to be the identity on the system. And we can see that easily if we just look at this definition. Mu dagger is 0 E U S E dagger mu mu U S E. Right? So this is M dagger, this is M. Sum over mu. This becomes this is the identity, I take it out. U dagger U is the identity, I get 1. Okay? So, we have this expression for unitary evolution, U dagger U is the identity. For a more general Krauss map, the sum of N dagger M's for all the mu's is the identity. Okay. So this is a trace preserving map. All right, very good. Now, I want to get under the hood a little bit more and the relationship of this to entanglement, okay? All right. Let's write down what's called the unitary representation of the map or the quantum channel. So let's say, in this case, let's look at the case that the system is in a pure state, okay? The system is in some pure state, let's just consider that to be the case. And the environment is in this fiducial state. And then there's some joint dynamics on the whole thing. So this is really just this that we wrote down earlier, but for the case of the system being in a pure state rather than a mixed state, okay? Now, if I insert a identity on the environment, which I can do as a sum over the basis states of the environment, and I multiply it on this, then I can take the partial matrix element on that, which is the Krauss operator. Okay, so what I did is I put this guy over here, and I took the partial matrix element, which we said was the Krauss operator. So let's look at that carefully. What this says is that, in general, when I apply this unitary operator to the joint system, I entangle them in this way. I entangle them in this particular representation, which says for every basis state in the environment, I apply, there's some operator M that gets applied to the system, okay? That is this is what's called the relative state representation, or the unitary state representation. It's very interesting. Yes?
Is it related to the decomposition?
It's interesting, it is related, and that's a very good question. We'll come back to that. It's an excellent question. We'll have to think about the carefully. Is this the truth decomposition? I'll come back to that in a moment. Okay. Now, so this is the joint state of the system and environment at a later time. It's this generally entangled state. It won't be entangling if the joint dynamics were separable, but generically it will be entangled. Okay. So the state of the system alone is the trace of, over the environment of the joint system environment state, and we recover the Krauss map that we had before. Everyone see that? If I just take the outer product with itself, and then I take the trace, I'm going to get the off-diagonal elements between M and M prime, between mu and mu prime will go away, and I'll get this expression. So what we see is that generically, this guy is mixed, right? Even if the initial state was pure. And why was it mixed? Because the system became entangled with the environment. And once the system is entangled with the environment and we don't have access to that information in the environment, we've lost information, we've increased entropy, the purity decreases, the system becomes mixed. So the disentanglement is exactly here. Now, what is the nature of that mixed state? Well, here it is, but we can write this in a slightly different way, and we'll come back to this in a moment. If we look at this, let's look at the state over here. So let's consider, let's go over the rule aside over here. And let's consider the state that I get when I apply the Krauss operator mu to the system of the state. Okay? That state is generally not going to have unit norm because this is not generally a unitary map. Only unitary operators preserve the norm. So I can write this in the following way. I'm going to call this state psi tilde sub mu. It's not normalized, okay? All right, that's fine. So if I do that, where this guy was this initial pure state, then the state at the later time is equal to this. Right? So that's the operation of mu on that is that. This for the system. Now these are not normalized, but I can renormalize it. I can define psi mu for the system as this divided by its norm. And that norm is equal to the square root of the inner product of that state with itself. Yes?
Sorry to go back to it, but at what point in the steps you took when you acted U on the initial pure state, at what specific step did that become a mixed state?
It's not. Okay, so let's be very clear about this. The total dynamics of everything in the universe is unitary, as far as we know. Which means that since I started this thing as some pure state, the joint state of the whole thing is pure, right? It's entangled generically, but pure. We see the system being now generically a mixed state because we traced over the environment. And so once we trace over the environment, and if the system were entangled, then the subsystem, which in this case is the system, will be mixed. Yes?
At what point does it become entangled? Because we're still working with a separable field.
No. That was just an example.
Oh.
So, I was just saying, if my dynamics was separable, then I wouldn't see it would be unitary dynamics and I would maintain purity. I'm assuming this to generically being an entangling unitary.
So where does the mu, the Krauss, come from? From the u?
Well, I mean, it is this, if I take, what I did is I put this guy over here and that guy, we had mu 0. That became the Krauss operator. Now that Krauss operator could be a unitary if it was separable, but it's not generically. Excellent. All right, so let's come back over here. And what do we see in this case? So I'm defining the state without the tilde as the renormalized version of the state, okay, when I applied the Krauss operator to it. And what is this? Well, this is equal to the square root of, according to this, psi, the initial state of the system, and mu dagger, and mu. Okay? So, I'm going to call this object the expectation value with respect to the initial state of the system. This is all the initial state of the system, as P mu. Why? Well, if I multiply top and bottom by the norm, this thing is then equal to the sum over mu, P mu, each one of these things, of course, is a function of time, because the Krauss operator is a function of time. But, so let's just write this down again. What we have is that at time t equals 0, I chose, in this particular case, the system to be in some pure state. At a later time, due to these entangling dynamics, once I trace out the environment, I get a mixed state. And that mixed state has the following form. Let's look at that form and understand it. What do we see in this? What we've said in this way is that the interaction with the environment prepared the system in a mixed state with ensemble decomposition P mu psi mu. So we remember that I can think about a pure state as a statistical mixture. I can think about a mixed state as a statistical mixture of pure states mixed by some probability, okay? These are not the eigenvalues and eigenvectors necessarily of the density matrix. These guys need not be orthogonal states. This is some ensemble decomposition. As you remember, we can make an ensemble decomposition out of any states we like and make a perfectly valid quantum state that is positive, okay? Where in this case, the ensemble is prepared in the following way: psi mu is equal to the action of the Krauss operator on the initial state and then renormalized, and that renormalization factor is the square root of P mu. That's what we have up there. And P mu is equal to that. Okay, yes?
Is there a specific condition where they're orthogonal and thus the eigenvalue?
Yeah, I mean, I'd have to think about that pretty carefully. It's not off the top of my head, but we certainly could derive such the situation. I'd have to think more carefully about that, Nate, but I don't know the answer off the top of my head. Right. So one way to understand and think about this is the following way: that we can think about a this kind of dynamics that leads us from initial pure state to a mixed state. So the open system dynamics is equivalent to what we call a measurement model. This is what we call a measurement model of open quantum system dynamics. What does that mean? We'll come back to talk a little bit better about more measurement probably on Thursday. But I can think about it in the following way. If I look at this situation, there's information about the system in the environment, because the environment and system are correlated. More than just correlated, they're entangled, right? So if we knew that the environment was in state mu, well then we can project onto that, and then the state of the system would be this, renormalized, okay? So stated again, what I'm saying is that the environment has information about the system. They are correlated. In fact, entangled. So, if we knew that the environment is in this state, then the state of the system conditioned on that, which we're calling psi mu, is equal to the Krauss operator acting on the system and then renormalized. Okay? So if we knew that, then the effect of the environment would be to apply this dynamic to the system. However, we don't know that the environment is in this, so we have to average over all the possibilities. And since if we don't know, but we don't know. And since we don't know the state of the environment, we have to trace over it, which is equivalent to averaging over all the possible mu's that could. Let me just finish and then I'll answer questions. We have to average, since we don't know what mu is. All we can do is say, well, we don't know what there is. It could have been this mu, it could have been that mu, and we have to then just weight that by the probability that that's what was happening. That probability is this. Okay, so Benny had a question first.
You just answered it.
Okay, and now allow my question.
So, I mean, the physical picture is basically, you make a process, and then you measure, and then it collapses to one state, and that's okay, right?
Yeah.
It collapses, like, when
If-
it collapses,
if-
it collapses to one state. You don't know which state.
If we were able to look at the environment and find that the environment was in state mu, then because of the entanglement and the spooky action at a distance associated with it, we would collapse the system into this state. Okay? But we didn't do that measurement. And because we don't do that measurement, we have to average over all the possible ones that could have been, weighted by the probability that that's what we would have found.
Right.
Yeah.
Yeah, that's good. But
Yeah.
I'm talking about experimental, like if you just measure it and it collapses to that state, and then the statistics of this just comes out like after you do so many measurements of this, that average, like that
Yeah,
asymmetric
well,
problem.
yeah.
Because every time you got a different state,
So,
with some probability.
yeah,
And you have
so
to
that,
understand the
that's what we're gonna talk about in a little while, the relationship of, so there's so many layers in this, and maybe I'll get to your question in a moment. Part of this is conceptual, okay? We conceptually, and it's an important conceptual idea, that an open quantum system dynamic is in some sense about how information in the system and environment become correlated and entangled. And why thus, if we don't have access or don't choose to have access to what's happening in the environment, then we will lose information, the system will become mixed. And the particular ensemble decomposition that we wrote down was given by, you know, the way in which we wrote this formalism. Yeah. But as you say, in principle, I can also think about, and we'll come back to that, what if I actually do know the state of the environment because I choose to measure it, and I can do that in some way. We'll come to that later. Yes, Nate, do you have a question?
Yeah, I was gonna ask, like, is this equivalent to like the notion of this, of measuring and then forgetting
Yeah.
the outcome?
That's right.
Okay.
Yep. Nate, you had a question?
The sum of all possible outcomes weighted with probability reminds me of the Feynman pattern rule.
I'm not sure. I mean, the difference here is that in a path interval, you have a coherent superposition of all these possibilities. This is more of this is a statistical mixture, so that's what's different here. But we'll also talk about the notion of a quantum trajectory, which is a little bit closer to a path interval. All right, now I want to come to Arik's question. So I can come back, let's write this thing. One of Eric's questions. Okay, because I just renormalized this by multiplying top and bottom by the square root of p. Okay. Is this the Schmidt decomposition? No.
Can we assume they're orthogonal?
No. That's why. If they were orthogonal, come back. I don't know the answer to this question again, but anyway, if they were, this would be the Schmidt. So generally, this is not the Schmidt decomposition. It's exactly what you're studying in your homework now. I hope you're working on it. The Jaynes-Cummings model, where we see the same kind of relative state evolution of the atom in the cavity. All right. Now, there's one, or there's a number of aspects of this. We lost 5 minutes from let's take that in. But anyway, so I chose a particular basis to expand our unitary representation of the channel in. We did that right over here. I mean, it's been erased, but I chose this basis mu as a way, right? But I can, in principle, choose any basis I like, okay? And that's related to the fact that, so, that there's an ambiguity here. Let's say we have a different basis, I'll call it nu. Well, so my joint evolution on the system and the environment, we said was this. But if I had a different basis, which which I can perfectly well use to describe the environment, then I have another representation of the unitary channel, where the relative state that's prepared is relative to a different basis, okay? Where n sub u is this cross operator. There's these two things are the same overall state, okay? If I look at the reduced density operator, in this case, we had this Krauss map, but it's equally well equal to this Krauss map. Does everyone agree with that? Yeah.
Is there any physical distinction whatsoever?
No.
No.
We'll come back to understanding, I'll say a little bit more about what these different ones mean. But this state is equal to this state. They're mathematically equal. So the Krauss operators that define the channel are not unique. What is the relationship between them that they can have? What is the constraint that relates them, that determines something? Yeah, Nate.
Do all of them still have to sum to identity?
Yeah, if at this point they were talking about trace preserving maps, so this is true, but also the sums. Now, let me just remind you of something here. So this we said was equal to a statistical mixture of states psi mu, where psi mu is mu acting on this and then renormalized. Similarly, this is some other statistical mixture where the psi mu's are equal to the n mu's acting on the state and then renormalized, where the q's are the probabilities given by the same expression we wrote down for the n's. So we remember, I'm sure we all remember, that the ensemble decomposition of a mixed state is not unique. I can statistically mix pure states in different ways and end up with the same mixed state. What is the condition that this mixed state equals that mixed state? There's an isometry kind of relationship. So you may remember that what we need, if I call, let me call these things just not to be confusing. These are, I'll call phi's. They're different letter. So the phi mu tilde has to equal some where the tilde is the unnormalized version of them, has to be where this thing is an isometry. If it's a square matrix, it's a unitary matrix, but in principle, actually, I don't even have to have the same number of elements in these two. I just have to have the rows and columns of these things. And that's equivalent to saying that nu is this matrix acting on this summed over mu. You know, I'm using the Einstein summation notation, right? So if my cross operators are related by an isometry or unitary transformation, then they represent the same quantum map. Okay. Now, I want to come back to the measurement model aspect of this. Why do these correspond to the same quantum map? Well, it's because, yes, there's information about the state of the system in the environment. And if I knew that the environment was in this particular state, then we would collapse to this state and we'd renormalize it. And if we knew that the environment was in this state, then we would collapse it to this. And these states are not equal. However, their statistical mixture is equal. And the reason they're equal is because we don't know. We didn't do a measurement on the environment. And since we didn't do a measurement on the environment, we have to average that. And those averages, those statistical mixtures are equal, as they must be because these states are the same. And we just did the partial trace. It's just a representation of that partial trace.
Do you think of this like you just mentioned the environment in a different basis?
That's correct.
Yeah, right.
That's correct. We could do a more general measurement of the environment in a more general POVMs. We'll talk about POVMs very soon. So I don't even have to have the same, this doesn't have to be a square matrix. There's some maximum number here and they don't even have to be the same. If it's an orthogonal basis, then yes, they have to be the same, the dimension of the environmental. But I could have more Krauss operators in one or the other, okay? But there's this intimate relationship between the Krauss map and the measurement model, okay? There's so much more to say, but I think I'm gonna stop it there. Anybody have any final questions before we end for the day? All right, very good. The notes are uploaded. I encourage you to read them, and we'll continue the discussion on Thursday.
Something mathematically convenient about the isometry and the logic.
Yeah.
At any point, if you have a rectangular matrix,
Yeah.